So let's start here. Make this a little bigger. Okay, so suppose you want to determine the area of the shaded region under a curve, okay, bound by the x-axis. So it's everything below the curve but above the x-axis. And typically, usually, you're going to be integrating from some x value to another x value. And that would give you like that shaded blue area you see under the curve in the first diagram. You can approximate the area of that shaded region by using rectangles. And what we do is we're going to sum, you add up the area of all the individual rectangles to determine an approximation of that actual shaded area. The sum or summing of these rectangles is often referred to what's called a Riemann sum. Okay, now if we look at the second diagram there, what's been done there is we've used 4 rectangles with the same width. So each one of those rectangles has the same width, but the heights differ. Okay, they're all different heights of rectangles. And if you were to add up the area of those rectangles, you would get a really rough approximation of the exact area. And you can see from that diagram, it's an under approximation or an underestimate of the actual area because you've still got all those light blue regions that aren't accounted for by the rectangles. So the rectangles cover most of the shaded blue area, but not all of it. So the question becomes, how do I make that approximation better? In other words, I want to have a real small area that's unaccounted for, almost nothing. So in that diagram there was 4 rectangles of equal width chosen, but that's a random number 4. I could have used 5 rectangles, I could use 10 rectangles, I could use 1,000,000 rectangles. So you can improve that approximation by using more rectangles. And you can see from the third diagram below, if we increase the number of rectangles, we increase the accuracy of the estimation. If you look at the bottom diagram on the right, you can see there's a lot more rectangles there. And we're getting closer and closer to covering the actual area that we're after. So the more rectangles you use, the more closely the approximation is to the actual area of the shaded region under the curve. So that's where we're going. That's the method, the mindset here is that we're going to use rectangles to approximate the actual area. So the first type of approximation, well, I've labeled it Riemann approximations, but it's fair to say that they're rectangular approximations because we're using rectangles. But before we can begin, okay, you have to determine how to position the rectangles in that actual area. Okay, so there are 3 ways that we can position the rectangles. And each one of those ways is a different way of approximating the area. Okay? The first method is called a left Riemann approximation method. Short form, LRAM. You can also use it as an acronym for left rectangular approximation. So whenever you see Riemann, rectangular is what we're after. We're using rectangles for the approximation method. So with the left Riemann approximation method, or with LRAM, what we do is we position the top left-hand corner of each rectangle on the graph of the function. So you can see in the diagram there, we used 4 rectangles, but the top left-hand corner of each rectangle is on the graph of the function, and that is what tells us or gives us the height of each rectangle. So you can see those top left-hand corners, you can measure the height to those dots from the x-axis. That would be the height of each rectangle. That's if we use the top left-hand corner. There's no reason why we couldn't use the top right-hand corner. So that's a little bit different. That would look like this. So now you've got 4 rectangles, but the height of each rectangle is dictated by the top right-hand corner, the position of the top right-hand corner of the rectangle. So it's that height above the x-axis of that top right-hand corner that gives us the height of each rectangle. The third method is a midpoint rectangular approximation method. And what we use there is the center of each rectangle would line up on the graph. And you can see from the diagram, the midpoint of each rectangle forms the height of each rectangle. So it's not the left or right corner, but it's right in the middle of that width that you line that up with the curve, and that forms the height. So you could write this as H1, this would be H2, this would be H3, and this would be H4. And they all line up in the middle of each rectangle. Any questions so far? So those are the 3 methods, and I'm going to cover them in detail with some examples. But before we do that, I just want to talk about what does it mean when we say partition or subdivision. So partition or subdivision just refers to the number of rectangles used to divide up that x interval. So from like here to there, we've partitioned that into 3 equal subintervals. Partition just means to split it up. Okay? So we're really just referring to the number of rectangles. Now you can use 2 different types of partitions or 2 different ways of splitting up the x interval. One is to use a uniform partition. A uniform partition just means that all the rectangles are going to have the same width. But there's no reason for them to all be the same width. We can use rectangles of all different sized widths. That would be a non-uniform partition. So in other words, you would be splitting up that distance along the x-axis using rectangles all with different widths. We're going to use uniform partitions because it's a lot easier. But it doesn't matter which one you use, you still arrive at the same idea in the end. Okay, but we're going to use uniform partition, so all our rectangles will have the same width. So here we'll go. We'll start off simple going through these examples. And I might need to make this smaller, but you're given a graph of y equals g of x. Okay. And we're being asked to approximate using LRAM the area between that graph and the x-axis, starting at x equals 2 all the way over to x equals 6. And you can see that area is shaded in. But it's really difficult to say exactly what that area is. But we're going to approximate it, first of all, using LRAM. using 4 equal subintervals. So, what does that mean? That means we're going to split up the distance between 2 and 6. So the width of each rectangle is 6 minus 2 divided by 4 because we're using 4 rectangles. So the width is just going to be 1. And so starting here, I'm going to, because I'm using LRAM, there's my first rectangle. Then I go and draw my next rectangle. I extend it up to the graph on the left-hand side. That forms the height right there. And remember, we're drawing rectangles, so it'll come down like that. The third rectangle, I go up and the left corner needs to be on the graph, so that would be there. Extend it down. Now I have my third rectangle. And my fourth rectangle would be here. Again, the left top corner is on the graph. We've got 1, 2, 3, 4 rectangles, all with the width of 1. So now if I want to approximate, if I want that area, all I need to do really from the diagram is count the boxes. So if I count the boxes, I get that the area is equal to 3 from the first rectangle plus 7 from the second rectangle plus 6 from the third rectangle plus 4 from the last rectangle. So our total area using LRAM is 20. Notice again the red dot is the top left hand corner of the rectangle lining up with the curve. Okay, part B says use RRAM to determine approximation for the area between the graph and the x-axis, again from x equals 2 to 6, using 4 equal subintervals. So again, W, the width of each rectangle is 1, but now I need to use RRAM. So I'm going to erase what I've drawn there, most of what I've drawn there. And now I need to draw rectangles such that the right-hand top corner lines up with the graph. So my first rectangle, I've got these two lines. That means that the right-hand side needs to line up and this top corner forms the height. So my first rectangle should look like that. Okay? Top right-hand corner lines up with the graph. Then I move to the next one. Top right-hand corner lines up with the graph. Next one, top right-hand corner lines up on the graph. And the last one, top right-hand corner lines up on the graph. So you can see the area is slightly different. But we can write an expression for that area just by adding up the squares. So the area using RRAM is, well, we can, if we wanted, I could write it's the area of rectangle 1 plus the area of rectangle 2 plus the area of rectangle 3 plus the area of rectangle 4. Rectangle 1 has, what, 7 units, plus 1, 2, 3, 4, 5, 6 for rectangle 2, 4 for rectangle 3, and 4 for rectangle 4, to give us a total of 21.
How do
Any questions on that? So that's how you use LRAM and RRAM. And in this case, we used 4 subintervals. You find your width, and you just line up the corner on the graph. Next example. Same idea. Use LRAM to determine approximation for the area between h of x and the x-axis from -2 to 4, but this time we're using 3 equal subintervals. Okay, so W, the width of each rectangle, is going to be the ending x value 4, subtract the starting x value -2, divided by the number of subintervals, or rectangles, which is 3. So W is 6 divided by 3, which is 2. Okay, so that means my rectangles, just kind of putting some red lines on there. Okay, LRAM, I'll start on the last rectangle. Okay, the left-hand side has to line up on the curve. So it would look like this. The middle rectangle, the left-hand side needs to line up on the curve. Would look like that. And the first rectangle is a bit odd. It's like this. It's 0. It has no area. So the expression for the area using LRAM would be 0 plus 8 plus 12. This has an area of 8. This has an area of 12, and the first rectangle isn't even a rectangle because it has 0 height. So that total is 20. Any questions on that? Okay, part B. Do the exact same thing, except now use RRAM. So a right rectangular approximation. So I'm going to get rid of my rectangles here. Okay. Now, the right top corner of each rectangle. So the first one would be way up here. The right corner forms the height, or gives me the height. The next one would be like this. Okay, again, top right hand corner. And the last one top right hand corner here. And now those numbers are no longer accurate, so let's get rid of those. So now I've got all this yellow shaded region approximating the blue area. Now this is obviously a really rough estimate, but I'm just trying to give you a sense of how this all works. So rectangle 1, 2, 4, 6, 8 has an area of 8. The next one has 12 if I count up those squares, 2, 4, 6, 8, 10, 12. And the last one, 8. So the area approximation using RRAM is 8 plus 12 plus 8, which is 28. And you can see there's quite a bit of difference between the left rectangular approximation and the right rectangular approximation. Not sure which one is more accurate because I don't know what the exact area is, but I know that I could make those approximations better if I used more rectangles. That just means more work, but it would definitely make the approximation better. Any questions on that one? Okay, the next example. Now, instead of being given a graph, you might be given a function, and in this case, I've kept it simple. Y equals, or f of x equals 2 to the x, okay? And we want to approximate the area under the graph from -3 to 3. Part A says using RRAM. So we're using RRAM with 3 equal subintervals. So we are going from here, -3, to here, 3, with 3 subintervals. So what's my width? My width is 3 subtract -3 divided by 3, which is 2. So the width of my rectangles is 2 units. Now if I'm using RRAM, let's see here. Use a different color. Then right here, the first one's going to be hard to see, but it's going to look something like that. Whoops, that was LRAM. We need RRAM. My bad. Let me erase that. This top right-hand corner gives us the height of the first rectangle. Then the top right-hand corner gives us the height of the second rectangle. And then this top right-hand corner here gives us the height of the third rectangle. Now, the area using RRAM is equal to the area of rectangle 1 plus the area of rectangle 2 plus the area of rectangle 3. The area of rectangle 1 is 2, which is our width, multiplied by the height. The height of rectangle 1 is f evaluated at -1. Add to that the area of rectangle 2. So again, this is the width, this is the height. For the next rectangle, the width is still 2, so it's 2 times the height. Now the height is just f at 1. In other words, this height here is f at 1. Again, this was the width, this was the height. Plus the area of the third rectangle, which is the width of 2 multiplied by the height. This height is f at 3. Again, the 2 is the width, and this is the height of the third rectangle. So now we're left with subbing all this business in. This is 2 times f at -1 is just 2 to the -1 plus 2 times f at 1 is just 2 to the power of 1 plus 2 times f at 3 is 2 cubed. So this is 2 times a half plus 2 times 2 plus 2 times 8. Final answer is 21. Okay, so if I were to shade in these rectangles, that area would be 21. And just from looking at it, I would say that that's an overestimate. Because look at all this extra area that's above the curve. So we could say that this is an overestimate. Any questions on that? Okay, now we're just...
No.
Beautiful. Now we're going to do the same thing, same function, 3 equal subintervals, but we're going to use LRAM. Okay, so we got to use the top left-hand corner with 3 subintervals. So again, from -3 to 3. Except this time we use the top left-hand corner. So if I draw my rectangles, maybe I'll start with the last one first. I get this. For the second one, I get this. And the third one is really hard to see because the diagram is too small, but I get that. So the top left-hand corner forms the height. Okay, so this height here is f at 1. This height here is f at -1. And the height of the first rectangle is f at -3. So let me write that all in here. Area approximation using LRAM. Again, it's just equal to the area of rectangle 1 plus the area of rectangle 2 plus the area of rectangle 3. That's equal to 2 times f at -3 plus 2 times f at -1 plus 2 times f at 1. Okay, again, the 2 is the width of each rectangle, and this is the height of each rectangle. F at -3, f at -1, f at 1. Now you're just left with subbing in numbers into the function. So it's 2 times 2 to the -3 plus 2 times 2 to the -1 plus 2 times 2 to the power of 1. So this is 2 times 1 over 8 plus 2 times a half plus 2 times 2, which is 4. Final answer, 5.25. And if I shade in my rectangles here in yellow, I can see that, my goodness, it's a huge underestimation. The first one was a big overestimation. This one is a huge underestimate. We're good with that? Okay, the last one of this example is asking us to use MRAM, so a midpoint rectangular approximation with 6 subintervals. So a partition with 6 rectangles. Again, from -3 to 3. So in this case, W is 3 subtract negative 3 divided by 6, which is just 1. So our rectangles are all going to have a width of 1. And I need to use the midpoint. So the midpoint of each subinterval is going to be like here for the last one, there for the second last one. Everywhere I draw these blue dots, from each one of those blue dots, I would go up to the function, and that is what forms my height of that rectangle. Because it's a midpoint approximation. So from the midpoint of each subinterval, I go up to the graph, and that's what forms the height. Okay, so this is going to be increasingly more difficult to draw here, but I think you get the idea, right? So I need an expression for that. Okay, how are we going to write an expression for that? Well, we've got 6 rectangles, so let's start there. Area MRAM, midpoint rectangular approximation, is the area of rectangle 1 plus the area of rectangle 2, rectangle 3, rectangle 4, plus the area of rectangle 5, plus the area of rectangle 6. Now I need to write an expression for all that. So the width is just 1. So for all of these, it's going to be 1 times. Now the height of the first rectangle, I get from evaluating the function not at -3 and not at -2, but right in the middle. So f at -2.5. Plus, again, the width is 1 times f at -1.5. Plus 1 times f at -0.5. I'm running out of room there. So plus 1 times f at 0.5 for the fourth rectangle. Then the fifth rectangle is 1 times f at 1.5 plus 1 times f at 2.5. Okay, so now for this one, you'll need a calculator. I've done the calculation. I got to sub in -2.5 into f, -1.5, -0.5, 0.5, 1.5, and 2.5. When I do all that, I would get a final answer of 11.136. Okay, so the area in that case, I can try and shade this in for you as well. So I'm using these rectangles. You can see that this diagram, this approximation is definitely much better than the first two. Right? I got that area there. Are there any questions? Okay, so there we've used the midpoint of each partition, of each rectangle to form the height. And that's it. That's the 3 rectangular methods. That's how they work. The next example. So I've got several examples here. The next example doesn't give us a graph, doesn't give us a function, but gives us a table of values. Okay, and it asks us to do RRAM, a right rectangular approximation, and then you're being asked to do a left rectangular approximation for this example. So the data is given to you with there are 4 points there. So if I have 4 points, and in part A, we're being asked to use a right rectangular approximation with 3 equal subintervals. Well, if you notice, the x values, the difference between the x values is uniform. Okay, so we're using 3 equal subintervals. Okay, here's the first subinterval, then the second subinterval, and here's the third subinterval, or rectangle if you like. So you can see the width of each one of our rectangles is 3 units. The first one goes from x equals 1 to 4, the second one goes from x equals 4 to 7, and the third rectangle extends from x equals 7 to 10. So an area approximation using RRAM, okay, what you're trying to do is visualize that you've got 3 rectangles. So I'm going to add up the areas of my rectangles, and there's 3 of them. Okay, the area of the first rectangle. So if I'm using RRAM, for my first rectangle, then this would be the height of the left-hand side of if I was using LRAM, but this would be the height, and I mean the y values now. We're looking at the y values. I would have to use 8 as the height of the first rectangle. So the area would be a width of 3 times a height of 8 because I'm using the right rectangular approximation. Then I erase that and I move to my second rectangle. Now I'm going to be looking at either 8 or 3 as my height. But because it's a right rectangular approximation, I'm going to use 3 as the height. So that would be a width of 3 times a height of 3. Again, this is width times height. This is width times height. And then for the last rectangle, if I erase this nonsense here, then I would be looking at one of those 2 as the height. The width is still 3, but because this is a right rectangular approximation, I'm using 5 as the height. So this is the width, this is the height. So I get 24 plus 9 plus 15. You add that up and you get 48. Now it's the same logic for part B. Okay. Again, we're using 3 equal subintervals, but we're using LRAM this time. So if I write this out, LRAM, I've still got 3 rectangles, so it's the area of rectangle 1 plus the area of rectangle 2 plus the area of rectangle 3. So that's going to be 3 times. Now, for my first rectangle, it's not going to be 8 as the height. 6 will be the height because I'm using an LRAM, a left rectangular approximation. Then for the second rectangle, yes, the width is 3. But now, for my height, I'm either going to choose 8 or 3, but because this is a left rectangular approximation, my height is going to be 8. Then I shift to my last rectangle, and my data points, my y values are either 3 or 5. That's left, that's right. I'm going to choose 3 as the height because 3 would be on the left. 5 would have been on the right. Again, this is width times height, width times height, width times height. So I get 18 plus 18. That's not 18. The first one is 18. 18 plus 24 plus 9 gives us a total of 51. So those approximations are pretty close to each other. One is 48 and one is 51. That's how you would go about doing rectangular approximations when you're given a table of values. In this case, the partition is uniform. In other words, the width of each rectangle is the same. That's the way it was given to us in the table. It doesn't have to be like that, but in this case it was. Any questions? Okay, next one. Again, another example with a table of values. This time, again, the partition is uniform. In other words, the difference between... So you form a rectangle with each adjacent point, but you can see that the widths are all the same. It's uniform. So we can say that W is equal to 0.5, right? It's exactly the same for every rectangle. Now, if I want to approximate the area using LRAM, okay, because how many rectangles am I going to have? I'm going to have 1, 2, 3, 4, 5, 6 rectangles. The width of every single one of those rectangles is a half. So it would make sense, because we like to cut down on the writing, why not just take 1/2 out front and just multiply it by every height, multiply it by the height of every rectangle. Instead of writing 0.5 6 times, we'll just write it once, and we'll multiply it by the height of each rectangle. So if I'm using LRAM, the height of the first rectangle will be 2. The height of the second rectangle will be 4. The third, 6, 7, 4, and 1. Those are the heights of each rectangle. The first one has a height of 2. The second one has a height of 4. Third one, 6. Fourth one, 7. Fifth one has a height of 4. And the last one would have a height of 1. Do that calculation and you'll get 12. Notice that we used all the Y values except the last one for LRAM. Now let's do RRAM. Again, we'll take out the 0.5 because the width is the same for every rectangle, except now the first height is not 2, the first height is 4. The second height would be 6. The third height would be 7. The fourth height would be 4. The fifth height would be 1. And the sixth height would be 5. So if you look at that, what's happened is we've used all the Y values except the first one. And we're going to multiply the sum of those by the width. And I believe we should get 13.5. So those approximations are close to one another. So you kind of see the pattern there. With LRAM, you use all the Y values but the last one, and for RRAM, we use all the Y values but the first one. Any questions on that? Okay, part C now says approximate the area under the graph using MRAM. So a midpoint rectangular approximation. We need to be careful with this one. Okay, so what I cannot do is I do not say that the midpoint between 0 and 0.5, let's just take a look at this. This is what you do not do. I don't say that the midpoint is 0.25 and then I don't know what the Y value is in the middle. Don't take an average. That's not how this works. You can only use the data in the table. You can't fabricate values from what's in the table. So what we have to do is we have to look at this a little bit different. We have to change the partition. So now, instead of having 6 rectangles, I'm only going to have 3. And the reason for that is because now if I do it like this, each partition will have a midpoint. This would be the midpoint of the first one, this would be the midpoint of the second one, and this would be the midpoint of the third one. So there's only 3 rectangles. That's the only way I can do this. Okay, so now my area approximation using MRAM is, so the width of each one of those, now the width is no longer a half. You can see that the width is equal to 1. Right? The first rectangle extends from 0 to 1. The second rectangle starts at 1 and ends at 2. And the third rectangle starts at x equals 2 and ends at 3. So the width is now 1. So I get 1.0 times, now the height of the rectangle is the Y value in the middle. So it's these values right here. 4 plus 7 plus 1. And if you add that up and multiply by 1, you get 12. Okay? So that's how you would do a midpoint given that table like that. Now sometimes you'll be given a table of values where you wouldn't be able to use midpoint. It doesn't work out using midpoint. And so if they ask you, you wouldn't be asked to find a midpoint. This one lends itself well to doing midpoint, but not all tables will. So, any questions on that? Time we got. Let's see here. What do we got next? Okay, I'm going to stop here. And we'll leave this for next time.